Hello everyone and welcome to uh, lecture 4 on an introduction to inorganic chemistry. We've spent some time discussing the way in which atoms pack in crystalline materials, and we've considered the bonding in these systems as largely ionic. That is, we usually have a cation and an anion. And I'd like to spend this session today by considering the energetics of ionic bonding and using Born-Haber cycles to calculate some of the parameters surrounding the energetics of ionic bonding, in particular trying to calculate the lattice enthalpies for crystalline materials from empirical data. And I'd like to have towards the end a very brief discussion on the relation of these theoretically calculated lattice enthalpies or values to experimentally determined values, and understand some of the implications if these two values are consistent or if they differ. Now, some of you will have studied the energetics of ionic bonding before at A level or in high school when you've been looking at Born-Haber cycles. I'm sure that you've all come across that on various courses previously. If you don't worry. Have a look at the directed reading for this lecture, and have a go at the practice problems at the end of this lecture. Now, let's have a little think about these crystal structures then, and some of the energetics that surround them. Atoms are like humans, they're lazy, and they will always adopt the crystal structure that corresponds to the lowest Gibbs energy. So look at the process that I show you in that generalized schematic on the left there. M plus X minus, both in the gaseous state, forming Mx in the solid state. Mx is our ionic crystalline material here, and we're considering its formation from two ions of opposing charge in the gaseous state, B to A, if you like. Now, when we consider the change in Gibbs energy that's associated with the formation of that solid crystalline material, if the change in Gibbs energy is negative on going from those two ions in the gaseous state to the crystalline material, then we can predict that the transformation is spontaneous, i.e. it happens readily. And we would expect the material to be found in that solid state with a structure that we understand. And you can think about sodium chloride, for example. At room temperature, it exists in the solid state in its crystalline form. It's more energetically favourable for sodium and chlorine to come together and form a solid crystalline lattice than it is for them to exist in the gaseous state at room temperature. And there's an equation at the bottom there which describes the change in Gibbs energy for a process, and that value, that change in G, delta G, must be negative for a process to spontaneously occur. And you'll note that there are two contributions then. There's an enthalpic contribution, a change in enthalpy associated with the process, and an entropic contribution, a change in entropy at a given temperature. Now, you can look at experiments of the formation of a solid from gaseous ions, and I encourage everyone to take a look at the YouTube video that I show you there. When you form a solid from gaseous ions, the reaction is incredibly exothermic. And for the compound that I show in that YouTube video, the reaction is so exothermic at room temperature that in that Gibbs equation I showed you on the previous slide and show you at the bottom there, we don't actually need to take into account the entropy change in the system, because the change in enthalpy is incredibly large. So it makes the change in entropy negligible, essentially. What that tells us is that upon the formation of this solid from gaseous ions, that reaction is so exothermic and it must release so much heat that we can ignore the change in entropy, which is very small. Now, when we're talking about solids, and in particular ionic solids, we tend to focus our discussions on these enthalpy changes. And you can see there's a table there from lithium fluoride right the way through to cerium oxide at the bottom of the periodic table. The key values there are the change in enthalpy that's associated with the formation of these solids. And we'll talk more about this on the next slide. We focus our discussions then on the change in lattice enthalpy. And there is a strict definition for lattice enthalpy. It's the standard molar enthalpy change accompanying the formation of a gas of ions from the solid. So you'll note that's the reverse process of what I introduced in the first slide. We're talking about going from a solid to the gaseous state. So have a look at again the generalized formula I show you there. We go from our Mx ionic solid with its crystalline lattice to the formation of two gaseous ions, the cation and the anion. And the lattice enthalpy then is a term that corresponds to the breaking up of the lattice. It's the energy that we've got to put in to break up the lattice and form gaseous ions. So it's a disruptive consideration. Therefore, the breakup of that lattice is always going to be an endothermic process. It's always going to take energy to break up a lattice. And therefore, the lattice enthalpy is a positive value. We can go one further then and start talking about the most stable form of a crystal structure, and we can use the lattice enthalpy to predict the most stable form of a crystal structure. And it's always going to be the one with the greatest lattice enthalpy under the prevailing conditions. That's because that's the compound or the crystal structure that we've got to put the most energy into in order to break up. Now, some of you will have come across Born-Haber cycles before. Here's an example of a Born-Haber cycle. We can determine the lattice enthalpy for a compound. In this case, I show you an example of potassium chloride from empirical data using a Born-Haber cycle. And what do I mean by empirical data? Well, this is data that we have access to readily in the textbooks or on the internet. So you can see the lattice enthalpy there is shown in the green arrow. At the bottom, I've got my solid potassium chloride. And if you go against the direction of the green arrow, you move to potassium and chlorine, both in the gaseous state. That's the value for my lattice enthalpy. So all we have to do to calculate that is to go the other way round the Born-Haber cycle, and I'll show you how this is done in a moment. So here's the Born-Haber cycle for potassium chloride, and you can see that there's lots of different values in there and a few different steps that we need to consider. And we'll go through these now. So my starting point in the Born-Haber cycle is the compound for which we are trying to calculate the lattice enthalpy. So it's potassium chloride here in the solid state. The top of my Born-Haber cycle then is here potassium, an electron, and chlorine. And to get up to that top point of my Born-Haber cycle, it requires energy. We've got to put energy in to break the lattice up. So the first step then is to split the elements up into their standard states under the prevailing conditions. Now, potassium is in the solid state under ambient conditions, and chlorine is in the gaseous state under standard conditions. And you'll note there I have to put half Cl2 because chlorine likes to exist as molecular chlorine. I then convert my potassium solid into a gas. I remove electrons from potassium to form the cation. And I split up the system into its constituent parts then. So that forms the top of my Born-Haber cycle. Finally, I make my Cl- ion by adding an electron to chlorine, and energy will be released in that process. And the lattice enthalpy then is this number here, the number that I'm trying to work out. I'm going from my two gaseous ions to my solid state crystalline lattice. Now, here are some values for the empirical data. I've got the sublimation of potassium there. I've got the ionization of potassium, the dissociation of Cl2, the electron gain by chlorine, and the formation of the KCl solid. These values of empirical data can be used in the Born-Haber cycle to calculate the lattice enthalpy for potassium chloride. So I've got to feed in the numbers here based on this empirical data. So I'm given the standard enthalpy of formation of potassium chloride as minus 438 kilojoules per mole. Apologies, it says minus 439 there. The standard enthalpy of formation is the enthalpy change during the formation of 1 mole of a substance from its constituent elements with all substances in their standard state. Well, that's exactly what I'm talking about on the first arrow on the left-hand side there at 438 kilojoules per mole. And you'll note that the value that's been given in the table of empirical data there is minus 438. That's for the enthalpy of formation. We're going in the opposite direction. We're going from potassium chloride to its elements in their standard state. So we're breaking up the lattice now. So we use the negative of the enthalpy of formation, which is, of course, plus 438. We're given the standard enthalpy of sublimation for potassium, which is plus 89 kilojoules per mole. So hopefully you can see how you can use, in an exam or a coursework style situation, you'd be given data, you'd be given the empirical data and asked to form the Born-Haber cycle and calculate the lattice enthalpy for the solid. You can use the empirical data that you're given to start thinking about constructing the Born-Haber cycle. We're also given the standard enthalpy formation of the ions here. So we are given the standard enthalpy of formation of gaseous potassium. in the ionic state. So you can think about that as the first ionization energy, basically. We are given the standard enthalpy of dissociation for molecular chlorine. So this is to gain our chlorine atom on its own, which is 244 kilojoules per mole. But look at the stoichiometry of the product. Potassium chloride only has one chlorine, so we've got to divide that number by 2. And we are given that electron gain by chlorine, which is negative 355. So all we've got to do then is follow the arrows around and input the values, add up the values to calculate the lattice enthalpy. So I take my 438 plus 89 plus 425 plus 122 minus 355, and it gives me the value of 719 kilojoules per mole. Now we can do exactly the same for something like magnesium chloride. There are the values that we take. So you'll notice you're given the standard enthalpy of formation for magnesium chloride as minus 524. We're going to use that in reverse, the standard enthalpy of decomposition. So that's plus 524. We're given the energy of sublimation for magnesium. So taking the magnesium solid into the gaseous state. We're given the ionization energy of magnesium to magnesium 2 plus. We are given the dissociation of Cl2 again, and finally the electron gain of chlorine. Note when we're given the dissociation of Cl2 as plus 244 kilojoules per mole, we keep that. We don't divide that by 2. That's because of the stoichiometry of the product having 2 chlorines. And we can calculate our lattice enthalpies by adding those values. Now, we can, the lattice enthalpy data that you see here is calculated from empirical data that has been obtained from experimental procedures. So things like electron gain by chlorine, things like the dissociation of chlorine, these are all experimental data. So the lattice enthalpy that we're calculating for these systems is based on empirical data, but that empirical data has been experimentally acquired. But it's also possible to theoretically calculate the lattice enthalpy. And if those two calculated values agree, then we can predict that our ionic model is a good model of bonding for that crystalline solid. If there is a large difference, then it suggests that there is a degree of covalency in the bonding for our solid, and we've got to invoke more covalent models. So we've got to start thinking about different covalent models of bonding. And the simple ionic model doesn't hold. The Born-Haber equation then is shown here, and it's used to estimate the lattice enthalpy for an ionic solid. And you can see that there are several contributions taken into account. There are Coulombic attractions and repulsions between ions, and there are repulsive interactions that occur when electron densities overlap. Importantly, I'm not going to ask you to employ this equation in an examination or coursework. I want you to have an appreciation that you can theoretically calculate these values. I will, however, expect you to be able to calculate the lattice enthalpy from the Born-Haber cycles. And you can see there I list all of the parameters that are found in the Born-Haber equation. Now look at the values here. You've got for a range of ionic solids, you've got the theoretically calculated change in lattice enthalpy and the experimentally calculated change in lattice enthalpy. And you've then got a difference between the two. You notice for lithium fluoride, the difference between the calculated and the experimentally derived lattice enthalpies is 1. Very, very low. We would therefore conclude from that the ionic model holds very well for a compound like lithium fluoride. However, if you look at silver iodide right at the bottom, the difference between the two lattice enthalpies is 105. And we would therefore conclude that there's a degree of covalency in the bonding model there, and we'd have to invoke other theories of bonding. So, as I said, good agreement between the experimentally and theoretically determined lattice enthalpies indicates that the ionic model is satisfactory to describe the bonding in a solid. Generally, we find the ionic model works well for atoms that have a cation and an anion that have relatively large electronegativity differences. Think about the electronegativity differences between lithium and chlorine. They have some of the largest electronegativity difference in the periodic table, being from completely opposite ends of the periodic table. The agreement tends to decrease as the polarizability of the ion increases. So the fact that iodine is more polarizable than fluorine, you have to invoke some kind of covalency in the bonding for compounds containing large polarizable ions. And we can use the data that we obtain from these calculations as a predictive tool. Now, have a go at the tutorial questions on the handout that's associated with this lecture. You can pause the video here and have a go at them, and I will go through the answers when you're ready. Just hit play again. So the lattice enthalpy for sodium chloride is 725.5 kilojoules per mole. And no real tricks here other than you've got to remember to consider the stoichiometry of sodium chloride. And the lattice enthalpy for magnesium bromide is 2,421 kilojoules per mole.